Hi everyone. Okay, today I'm going to talk about the precision in our measured and calculated data. So let's start with the rules that you see on the screen. I can break down data into two big chunks. The first one will be measured data. Measured data, as the name implies, refers to data that we get directly from instrument. So the data that we get directly from instrument, we need to follow the precision of the instrument. So in your Newton's second law practical, examples of measured data will be your delta x, which is a displacement that your cart has moved. You got this directly from a ruler measurement. So therefore, example of a measurement will be say 81.1 cm. Alright, it's one decimal place. That's the limit to what a ruler can read. And if you convert it to meters, you're going to get 0.811 meters. And in meters, the precision of your displacement of your length measurement will then become 3 decimal places. Another measured data in your Newton's second law practical will be your time interval, which you measured using a stopwatch. So an example of a time measurement data will be perhaps say 9.25 seconds, and this is corrected to 2 decimal places as indicated on the display of the stopwatch. A final example of measured data will be the mass of the cards, which you measure using the digital balance. Depending on the balance that you use, you are going to get something like this: 254.12 grams. Some balances in IS Lab can give you 3 decimal places in terms of grams, but in this case I'm writing 2 decimal places for one of the balances that we have in IS Lab. Similarly, if you convert it to kilogram, you're going to get 0.25412 kilogram, and this is now corrected to 5 decimal places. Note that conversion of units from grams to kilograms or from cm to meters shouldn't change the precision of your data. The number of decimal places that you write differs definitely because of conversion in units, but notice that all the numbers that I have written down for 254.12 remains as 0.25412. So changing of units shouldn't change the precision of your instrument. Now let's move on to calculated data. So a first example of a calculated data would be M, where M is the total mass of the mass of the card, the mass of the masses that you put on the cards, and the mass that you hang at the end of the string. So this is an addition, it's a calculated data, so we follow the least dp rule. So a typical data that you should have is here. So I get 0.25412 kilogram. If you do primary school math, then you should get this. Hanging masses, say I put in 3 masses on top, so I'm gonna get 150 grams. Converted to kg, I will get 0.150 kg, and that's it. I do not know the next 2 digits because the hanging mass just prints 50 gram each without any decimal places. Now finally, my hanging mass is a 50 gram mass, so I will add a 0.050. Similarly, I do not know the last 2 digits, and if I sum this up, there's no way I can know the last 2 digits because 2 of these data only have 3 dp here. Even though my first data mass of the card has 5 dp, I simply do not know what happens to the last 2 dp after I sum up all the masses. Therefore, as you can see, we keep our mass reading to the least dp, which is in this case 3 decimal places. So a typical example of the total mass if my mass of the card is roughly 250 grams, I add 100 grams worth of MA, I add 50 gram hanging mass. I'm looking at roughly 421 gram. So in terms of kg, I should get 0.421 kg. Alright, let's keep this mass value now. Another calculated data will be our quantity 1 over m. Now 1 over m is a calculated data. It is an inverse operation, so you should follow the least SF of the data. A typical mass value as shown above is 0.421, and this guy over here has 3 SF. Therefore, our value for the corresponding 1 over m should also be kept to 3 significant figures. Now, finally, let's look at our last calculated data, which is acceleration. So you should have worked out the formula for acceleration. For calculating acceleration, you need 2 times the displacement divided by the time interval squared. So again, this is also a calculated data. You need to look at the number of SF for displacement, which is shown here. In this case, 0.811 meters has 3 significant figures, so I'll just write it down here, 3 SF to remind myself. And the time interval should be roughly less than 10 seconds, so I'm looking at again 3 significant figures. So in this case, the least SF that I have here is 3 SF. Therefore, my acceleration data should be kept to 3 significant figures. Now, a lot of you have asked me whether the average time interval, do I consider it as a calculation? Because there's a division included in my workings to get the average time value. So do I follow the least SF rule? Well, the answer is no. Average quantity refers to the measured time interval in this case. The act of finding the average, yes, it does involve a division. So in that regard, I can argue that it's a calculated quantity. However, the average time interval is also a time measurement. You need not find this average time measurement. It's because you want to improve your data, you want to reduce certain, maybe human errors. That's why you take the extra steps to find more time interval, and then you take an average of it. After all, the average time interval here is still a time measurement. So it follows the time measurement, it follows the measurement rule, where you look at the least, or rather you look at the precision of your instrument. Therefore, for all your time or average time values, keep in mind average values are still measurement values, so they follow the precision of the instrument, in this case the stopwatch. Therefore, average time interval should be kept to 2 decimal places. So with this in mind, just bear in mind these 3 rules to tell you how many digits to write for your data. If it's a measured data that you collect directly from an instrument, just follow the precision of the instrument in terms of the DP given. If it's a calculated data, ask yourself whether is it addition or subtraction calculation. If it's so, you follow the least DP of your raw data. If your calculated data includes any other operations, it can be log, it can be exponential, sine, inverse, so on and so forth. A general rule is to follow the least SF given in our data. And a final learning point here is average quantity. Refer to it as a measured data. So any average quantity, you have to record it correct to the precision of the instrument.